Okay, so we're going to look at the last application of de Moivre's theorem that we have. And it's for finding the nth roots of a complex number. So I suppose the first thing to remember here is that if we have, say, the square root of a, that's the same as a to the power of a half. If we have the cubed root of a, that's going to be a to the power of a third, and so on and so forth. So we can rewrite roots as powers. And that allows us then to use de Moivre's theorem because we're writing them as a power. Now, when we're doing this, we have to adjust slightly because you'll even notice we said earlier that when we were working those powers of de Moivre's theorem that n was going to be an integer. Whereas now we're looking at opportunities where we're using a power but the power itself is not an integer because we're looking then at fractions. So when we're finding powers or roots, I suppose, of complex numbers, we have to rewrite the complex number in general polar form. And general polar form is what we have here. So general polar form is where we make use of the fact that cosine and sine are periodic functions and they repeat every 2 pi. So we know this from trigonometry that the period of cosine and sine is 2 pi. So what we're making use of with this general polar form then is when we want to find more than one solution. So when we're finding roots, we're generally going to be finding however many solutions there are will kind of line up with whatever root we're looking for. So if we're finding a square root, power of a half, we should have 2 solutions. If we're finding a cubed root, power of 3, we're going to find 3 solutions. If we're finding a fourth root, it's going to be the power of a quarter, we're going to find 4 solutions. And this adding on that period allows us to have those extra solutions. So we write our complex number in general polar form, we apply de Moivre's theorem, and then we're going to start with n equals to 0 and add up for however many solutions we need. So that's just kind of what we're going through here. Power 6th root has 6 solutions, so on and so forth. So let's just see how it looks in practice. So the question says z squared is equal to 1 plus root 3i. So first of all, we need to try and write this into polar form. And then we're even going to go further and write it into general polar form. So 1 plus root 3i is going to be here. I can write in my alpha here, and I can make note as well that I have theta here, and that's going to be positive. My modulus is 1 squared plus root 3 squared, which is 1 plus 3, which is root 4, which is 2. Getting my angle then, that's going to be root 3 over 1. Again, we keep seeing this kind of tan of root 3, but it's because it gives us a nice kind of clean number of pi over 3. And for this question, because of where the angle is, theta is just going to be the same. Theta is just equal to alpha. So theta pi over 3. And we can rewrite z squared then as 2 cos pi over 3 plus I sine pi over 3. Now, in order to find the root of this one, we need to write it in general polar form. So we have to write it in general polar form. So that means that z squared is going to be 2 cos pi over 3 plus 2 pi n plus I sine pi over 3 plus 2 pi n. Okay. Now, obviously we want to find the value of z. That's what we're looking for in the question. So that's going to be all of this complex number to the power of half. So let's just lay this out for ourselves first of all. We'll just kind of write that part down. So we're taking this whole complex number that we have here, pi over 3 plus 2 pi n, all to the power of a half. Now we're going to apply. So z is 2 to the power of a half. So that's just going to be root 2 cos a half times pi over 3 plus 2 pi n plus I sine a half times pi over 3 plus 2 pi n. Okay. So continuing on then, we're going to start with n equals to 0. We start with n equals to 0. Now, looking that we're getting a square root as well, we're only going to have 2 solutions. So we start with n equals to 0. That's going to give me z equals root 2 cos of, let me see, that will work out to be pi over 6 plus I sine pi pi over 6. So looking at that there, the 2 pi n, if n is 0, that's just 0. So it's a half just multiplied by pi over 3, which gives me the pi over 6 there. And we were asked here to give our answer in no particular form, just to find z. But we've kind of, the question was in rectangular form, so we'll go that extra step and we'll write our answer in rectangular form also. So let's just work out the value of that. So cos of pi over 6 is root 3 over 2. So root 2 by root 3 over 2. And we can work out what sine of pi over 6 is also. It is a half. And we get then, let's just compute this here, just particularly if we're a little unsure. So let's multiply by root 2 and see what we get. So we just get root 3 over 2, which is perfect. So root 3 over 2 plus root 2 over 2 I as our complex number there. So that's perfect. And let's just continue on and let n be equal to 1. And we get then that z is root 2 cos, let's see, it's going to be a half times, and let's see, the pi over 3 plus 2 pi is going to give me, well, let's just compute it here. So it's 2 plus a third, which is 7 over 3. So 7 pi over 3 plus I sine, and the same thing again here, a half times 7 pi over 3. So z is root 2 cos 7 pi over 6 plus I sine 7 pi over 6. And again, we'll go that step further and we'll just rewrite it in our kind of, I suppose, our rectangular form. Minus root 3 over 2 plus, and then our sine, I suppose, is going to be the same as the last time, minus a half. Yeah. Okay, and the root 2 in front, so we get that z is minus root 3 over 2 minus root 2 over 2i. And those are our two answers that we have there. So again, two solutions because we're doing to the power of 2. We're looking for, I suppose, z squared. Don't know why this fashion. We're looking for z squared, or we're looking for z. We're given z squared. We're finding the square root, so two solutions. Let's just look then at another example. This time we're going to be finding 4 solutions. So giving ourselves a bit more work, but that's okay. Let's lay it out in polar form first of all. Our answer is going to be over in this section here. This is going to be a, this will be our minus our theta here, and it's going to be negative. Let's find our modulus first of all as per. And again, you kind of see that a lot of this just becomes kind of the same kind of questions time and time again. Kind of you're doing the same steps all the time. So tan alpha being 2 root 3 over 2, we get the same thing as we've been getting, tan inverse of root 3. I should really know what it is at this point. It is pi over 3. Now for this one, we have to be careful. Theta is going to be negative, and it's also going to be pi minus alpha. So that kind of combines together to give me a value of theta as minus, let me see, minus 2 pi over 3. Minus 2 pi over 3. Okay, so I can lay out my complex number then. Z to the power of 4 is 4 cos minus 2 pi over 3 plus I sine minus 2 pi over 3. Okay, we need to go that step further now this time. So we're looking to find what Z is. That's going to be 4 to the power of a quarter cos a quarter. Sorry, I've forgotten our step in between. We need to rewrite in general polar form. There's one somewhere. So let's go again. So writing in general polar form, then we're including that 2 pi. So 2 pi over 3 plus 2 pi n plus I sine minus 2 pi over 3 plus 2 pi n. Okay, now we can go ahead and get our 4 to the power of a quarter cos a quarter times minus 2 pi over 3 plus 2 pi n plus I sine a quarter times minus 2 pi over 3 plus 2 pi n. So continuing on to the power of a quarter, and we need to just kind of set up now. So that's kind of our general polar form ready to go. De Moivre's theorem applied, kind of just the whole thing kind of ready to happen there. So we just need to look now at what happens when we do the values of n, I suppose. So let me just make sure I'm in the right place there. So n equals 0 first of all. So we get z is 4 to the power of a quarter. Cos, let me see now, if I have n equals 0, this part is just going to be 0. So I'm going to get a kind of total of minus pi, will be minus 2 pi over 12, which is the same as minus pi over 6. Minus 2 pi over 12. And were we asked in any particular form? We were not. So we can leave it in that form, or we can work it out further. 4 to the power of a quarter works out being root 2. We can double check that for ourselves here if we're just not sure. So let's just work out, and we can see we get root 2 there. Okay, cos to the power of minus 2 pi over 12 is root 3. And we'll do the same with the sine then. Minus a half. And we can multiply across by my root 2 there as well to get root 6 minus root 2 over 2 pi. Okay, as our answer there. Root 2. Now let me just double check and make sure we haven't gone astray there. Yes, root 3 over 2, sorry. Took that one and just our 2. There we go. I was thinking it's somewhere gone wrong there. Okay, so root 6 over 2 minus root 2 over 2 I. Gorge. Okay, doing these too late. Let's go with n is equal to 1. So z is equal to 4 to the power of a quarter. Cos, let's see, let's fill this in here. So we have a quarter times, so minus 2 pi over 3 plus 2 pi. So let's have a look at what that's going to leave us with. So it's 2. If we just kind of look at the fractions, 2 take away 2 over 3 gives me 4 over 3. So I'm going to have 4 pi over 3 here. And the same thing here. I sine a quarter times 4 pi over 3. Let's work this out now. So again, root 2 cos of pi over 3 plus I sine of pi over 3. And then we can actually work out those values. So cos of pi over 3 is a half. Root 2 times a half. And then sine of that is root 3 over 2. So we get an answer of root 2 over 2 plus root 6 over 2 I. Okay, still not finished because we're doing power of 4, so we have to do n is equal to 2 now. Just keeps going. Root 2 cos of a quarter times, well, let's have a look at what we're kind of computing here. So 2 pi by 2 gives you 4 pi. So 4 pi minus 2 over 3. So 4 minus 2 over 3 gives you a value of 10 over 3. So 10 pi over 3 plus I sine 10 pi over 3. So we get z is root 2. Let's keep going. Cos 10 pi over 12 plus I sine 10 pi over 12. So we can work out those values now. So cos of 10 pi over 12 and sine of 10 pi over 12. So let's work those out. Cos of 10 pi over 12 is minus root 3 over 2. And sine of that is a half. And multiplying that root 2 across, we get minus root 6 over 2 plus root 2 over 2i. And lastly, we have n is equal to 3 root 2 cos, again, a quarter times, well, let's go back again and have a look. So if n is equal to 3, that's going to be 6 pi, take away 2 over 3. So 6 take away 2 over 3 gives me 16 over 3. So 16 pi over 3 plus I sine, and again a quarter times 16 pi over 3. So z is root 2 cos 4 pi over 3 plus I sine 4 pi over 3, which means that z is root 2 times, let's fill those values in, so cos of 4 pi over 3 minus a half, and sine of that is minus root 3 over 2 I. We get that z then is minus root 2 over 2 minus root 6 over 2 I. Okay, so loads of values, loads of answers for z. So that's kind of the longest, I suppose, type we could get, unless you get kind of more powers. But if we even just look, we might kind of go through, because in terms of the exam questions, then there's just kind of more repetition of the same ideas happening with those ones. But if we just look at the examples that we have for them here, the exam questions find the 3 roots. The next one then was squared, so finding 2 roots, and the last one again is squared, finding 2 roots. So we might just look very, very quickly at this example here, just so we could see how we would set it up. So the same idea again, we would set it up, lay out our example here, our minus 8, it's just over on this side here. Our radius is just going to be minus 8 squared, so our radius is just 8. Our angle, we can immediately go to theta being pi. I can lay out my complex number then being 8 cos pi plus I sine pi. And so that's z cubed, obviously. We can write it in general polar form. So it's 8 cos pi plus 2 pi n plus I sine pi plus 2 pi n. Okay, and now again we're trying to get the kind of cubed roots of that, I suppose. So it's 8 to the power of a third cos a third times pi plus 2 pi n plus I sine a third times pi plus 2 pi n. So let's keep going. So 8 to the power of a third, the cubed root of it is 2. Why is that flashing? Unclear. Okay, so we're starting here with n is equal to 1. Let's just make a note of that. So starting here with n is equal to 1, that's going to be cos to the power of pi over 3 plus I sine pi over 3. And as per, we can compute those values. Cos of pi over 3 gives me a half, so it's 2 times a half, and sine of pi over 3 is root 3 over 2. And computing those values, we get 1 plus root 3 I. Next, going n equals 1, z equals 2 cos, and let's have a look at this one. So it's a third multiplied by pi plus 2 pi, which is 3 pi, and the same thing here, I sine a third times 3 pi. We can then work that value out, 2 cos times pi plus I sine pi, which means 2, and we can work out those values. And again, ones that we might be aware of, cos of pi is minus 1, sine of pi, we should know as well, is just going to be 0. 0I, so we just get a value of minus 2. And then when n is equal to 2, z 2 cos, again, a third times, well, let's go back and look. So 2, if n is 2, that's 4 pi, so 5 pi in total. And same thing over here, I sine a third times 5 pi, which gives me that z is 2 times cos 5 pi over 3 plus I sine 5 pi over 3. And we get that z then is, so work that out, 5 pi over 3 gives me a half. Same with sine here. Decimals, minus root 3 over 2. Okay, and that gives me 1 minus root 3I. And those are again my 3 values for Z my 3 solutions. So again, you can kind of see it's the same method each time. It just gets a little bit tedious kind of following through, and the same idea, particularly depending how many powers you have. You can kind of see there, it gets kind of long-winded. But laying it out again, the same as we've had with everything so far, laying it out nice and clearly, nice and straightforwardly, nice and steady, and not kind of jumping steps at any point. Just keeping it really, really consistent kind of lets us then work out those powers. But those are our 3 applications of de Moivre's theorem then. So the powers, the general powers, the trigonometric, the kind of multi-angle formulas, and now the roots of the nth roots of complex numbers. Those are kind of the 3 that you need to know of.